Hey everyone, welcome to our next section. Here we're going to be going through determining the number of x-intercepts, and we're going to be mostly using this idea of A and Q. So just to recap, A and Q come from our vertex equation, and our vertex equation, or our form here, is just y is equal to A, x minus p squared plus q. So here really we're going to be looking at the A value, and we're going to be looking at the Q value, mostly to kind of understand how we can visualize the general position and shape based on the values of A and Q. So this video is going to be a little bit different than the other ones, where we don't necessarily have to find an actual value, we just need to figure out how many roots it has. So what we'll start to see here is that there's a little bit of terminology that you would have hopefully learned before, but if not, that's okay, because x-intercepts, remember all of this happens when we talk about the function equaling 0. So x-intercepts are also sometimes called the roots of a function, and yet another name for it is to be called the zeros of a function. Okay, so roots or zeros or x-intercepts, they're all talking about the same thing. And basically that happens, and we can see it happens here, and both of those happen when y equals 0. Okay, so we can find those x-intercepts. Now, in this video, we're going to mostly just be talking about deciding how many there are, not exactly figuring out, like in this example, for instance, saying -1 and 3, but just saying that there are 2 roots. So we can have 2 x-intercepts in this case, where r and s are different values. So this would be in our factored form. We can see r and s have different values. This has a minimum and opens upward, and it's below the x-axis. Likewise, I could have a maximum point and have it open downward. If I started above the x-axis, it would have 2 roots. I could have 1 x-intercept in this case if my r value in this case is the same. And so in factored form, basically this is saying x minus r squared, or in vertex form, I could have y is equal to a x minus p squared, okay, where it just has one distinct root. Or we might have no x-intercepts, where I have a minimum value but it's above the x-axis and it opens up. Or maybe I have a maximum value that opens downward, but it's below the x-axis to start, and so I would have no way of it crossing the x-axis, so it would have no roots. So 2 parts, 2 distinct real roots. 1 part has 2 equal real roots, basically it's the same number twice. Or 2 distinct complex roots if it has no answer whatsoever for no real roots crossing the x-axis. We don't need to so much know about this complex part just yet. For those of you that are kind of move on and take further math courses down the road, you'll get into complex numbers at a different time. So for our next thing here, we're going to determine the number of x-intercepts using A and Q. So there's a couple of graphs that are set up here, and basically what I would like for you to do is to sketch out each one and tell me if there are 0, 1, or 2 x-intercepts. So pause the video, give it a try, and come back when you're ready. Alright, so with this one, remember that we have our equation in vertex form. I'll just sketch it over here. So y is equal to a x minus p squared plus q. And so my vertex here, notice that there's no p value here. So it's 0, -3, because q is -3. That means I'm moving down to this coordinate point at 0, -3. And I can see my a value here is a positive value, so that means that this moves upward. And I can see because of that, it's going to have 2 distinct roots. So I would say my answer here is probably 2. In my B question, I can see my p value here is just 1, and the q value is going to be 0. There's no q after this whatsoever. And so I'm going to move over 1, and then I can see that my a value is positive again, so this thing is going to open upward. And I can see that it has one spot where it crosses the x-axis, where p is 1 in both cases. So it kind of has one distinct real root to it. And in the C question, I've got a p-value of -2, and I've got a q-value of -1. So in this question, -2, -1 puts me here for my vertex, but then my a value here is a negative, and so that negative means that it opens downward. So if it opens down, this will never cross the x-axis, and so I would say that I have 0 roots here. So we can go ahead and go through and just double check those, just make sure that we're on the right track. And see here that I've got 2, 1, and 0. So a kind of summary of this, this would be something that might be helpful for you to jot into your book, just as kind of a guide to follow. So the value of a, if a is greater than 0, then the graph opens upward. If q is less than 0, then the vertex is below the x-axis. So those are the cases you have two distinct roots. Likewise, I could have a being less than 0 and q being greater than 0, and I end up with the same thing in terms of the two distinct roots. So my value of a in my next part is kind of this idea of visualizing the graph. So if a is greater than 0 and q is equal to 0, remember q is my up and down, so if q is 0 and it's right on the x-axis, doesn't matter if it opens up or down, it's going to have one distinct root. It's going to cross the x-axis at one spot, and that spot's the vertex. So in this case, this might even be helpful here. To visualize the graph, it touches the x-axis once, since the vertex is on the x-axis. So the vertex is the root in this case. And in the last one, just as an example here, let's say that q is less than 0, which means that it's below the x-axis, and then a is less than 0. It's going to open downward, and then in this case, there are no real roots. Likewise, q could be greater than 0, and a could be greater than 0, and then I'd have this scenario up top where I'd have a minimum and would also have no real roots. So, in summary, you can kind of see here how you can have three different graphs. My yellow line has that one distinct root at -3, 0, which also makes it the vertex. My green line has two spots where it crosses the x-intercepts, so you can kind of see how those two x-intercepts give you two distinct roots. And then the purple line in this case is below, and so it only has, has no roots, has only complex roots. So I've got one other example here for a little bit more practice. So determine the number of x-intercepts for each quadratic function without graphing this time if we can visualize this. So I'll give you a second, just try each one out without graphing and see how you can make out with finding the different roots. So pause the video and just give it a try. Alright, so keeping in mind of our form, okay, y is equal to a x minus p squared plus q, and kind of visualizing the idea here that we have something that's 0, -7, so we can picture this not going left or right at all, but going down 7 on our graph, and it opens upward, so basically it's going to go like this, right? And I know it says not to go through the graphing part of it, to graph it out in detail, but we can kind of see what this is going to look like just to make that a little bit neater. So we would say that this has two roots. In B, I can see here that my vertex is going to be -1, and then there's no q, so it's 0. This moves left one spot, but not up or down at all. This is only going to have one root, because the vertex is going to equal the root. And in my last one, I'm -5, -11, or sorry, +5, -11. And so in this case, I'm going to go right, and then I'm going to go down, and this thing's going to open down. And so because A and Q are both kind of in the same direction, they're both small, and I'm going to have no roots in this one, and only two complex roots as solutions. So 2 roots, 1 root, and no roots. Right? So that's the end for this video. There are If you check the website, you should notice a couple things that kind of go along with this. They're pretty small, and so let me know if you have any questions.